Section 22.8, Mutual Inductance and Self-Inductance. We'll start with mutual inductance. Mutual inductance is when you have two coils next to each other. Say one coil, the primary coil, is connected to an AC generator, so it has a changing current. Well, it turns out the changing current in the primary coil will then create a changing magnetic flux through the secondary coil, and that leads to an induced EMF in the secondary coil. Right, if we look at the AC generator, it's creating a current that's constantly changing. Since the current's constantly changing, the magnetic field created by this coil is constantly changing, and the coil nearby feels that and creates an EMF in response. So this is in effect known as mutual induction. And you can calculate the EMF that's induced based on Faraday's law, right? Negative N times the number of turns times the change in flux divided by the change in time. But for mutual induction, we can get a little more specific here. And the EMF due to mutual induction is that in the secondary coil, the EMF induced will be negative M. That's the mutual inductance. That's a constant based upon the setup of the coils, times the change in the current in the primary coil. Notice the P subscript is for the primary coil's current, divided by the change in time. And that will tell you how much EMF is induced. This mutual inductance, it has units of volts times seconds per amp. Basically, it cancels out the amps in the current and the time, the seconds in the denominator to get us to volts. And it's defined as something known as Henrys or Henry. I'm not sure the exact pronunciation. I just say Henry, which is a capital H, after the scientist Henry, who discovered this effect. So this is already kind of strange that you can have these two coils next to each other that are, one is directly influencing the other, right? The secondary coil is picking up what the primary one is putting down. But turns out it gets even stranger. And that's that there's something known as self-inductance. If you just have a single coil that has a changing current passing through it, that changing current will induce an EMF in the same circuit. This is known as self-inductance. We have an AC generator creating a current passing through the coil. That current produces magnetic field lines that are constantly changing as the current changes, and an EMF is then induced. We can then calculate the EMF induced with something very similar to our mutual inductance equation, but instead of the mutual inductance constant, we'll have a self-inductance constant, L, which just tells you about the coil itself, how it is wired, times the change in the current, divided by the change in time. And self-inductance has the same units as mutual inductance, again in our Henrys. So self-inductance is the basic idea behind an inductor, which is something that's used in a lot of circuits. It produces some interesting effects, which we will get to see, I think, in the next chapter. So we will see this again, but it's pretty wild that it happens anytime you have a coil within a circuit that has a changing current. You start to see these effects. One of the reasons why we care about inductors, which is just a coil, is that an inductor can store energy. So we can calculate the energy stored in an inductor with 1/2 the self-inductance times the current squared. Or we can even calculate the energy density with 1/2 mu naught, which is our permeability of free space constant, times the magnetic field squared. So inductors have some similarities to capacitors, it turns out. So if you notice, these equations look somewhat similar to our capacitance equations for the energy stored in a capacitor, the energy density there. That's because they're somewhat related in storing energy and then releasing energy in another way. So this is another important circuit connection. And there's a key application of mutual inductance and self-inductance, which we will see in the very next section.